Welcome back. Let me introduce our next speaker, Martin Schlipf. Martin Schlipf joined the VASP developer team in 2018. He works on implementing post-processing tools and quantum Monte Carlo methods for VASP. A great example of his work is the new Python tool, Py4VASP. If all goes well, we will release Py4VASP to the VASP community in February 2022. His talk is about a central issue in condensed matter. That is symmetry and sampling in reciprocal space. Martin, please go ahead.
Thank you for the nice introduction. So in this talk, or in this lecture, I will expand a bit on the lecture of Martin and go a bit more in depth about how the K-point grid in VASP is chosen, how symmetry affects the K-point mesh, and what considerations you as a user need to do when you choose your K-point meshes. So let's briefly recap what a K-point mesh is, where it comes from, what a reciprocal lattice constitutes, and let's look at this particular example. So for this lecture, I will always consider everything or represent everything as a 2D cell. So you can imagine that the third dimension of the cell points out of the plane, and then two lattice vectors are that remain in the plane of the slides. And now let's construct a reciprocal lattice vector of this particular cell. So we know that the reciprocal lattice vectors are given as a cross product of the real space lattice vectors, and in this case with the cross product with the out of plane lattice vector gives you this long lattice vector along this direction. And if you calculate the same lattice vector for the other direction, then you get the second reciprocal lattice vector in this direction. And this spans then the reciprocal unit cell. And then one important thing that you see here is that long directions in real space correspond to short directions in reciprocal space, and vice versa. So the short direction in real space becomes a long direction in reciprocal space. And this also holds for interactions. So interactions that are long range in real space get short range in reciprocal space, and interactions that are short range in real space are long range in reciprocal space. So now why do we actually introduce this reciprocal space? So here I attacked this problem from a slightly different angle than Martin did in his lecture. So we want to understand why we can describe the system by K-points and where this comes from. And all of this comes from the fact that in a crystal, everything is translational invariant with respect to crystal lattice vectors. So in a more mathematical way, this is expressed as the Hamiltonian commutes with your translational operator. And the Hamiltonian in this case has eigenstates. So these eigenstates have an eigenvalue epsilon and a band index n. And the translational operator just, if you apply it to a function, it will just translate this function by this real space lattice vector. And now we can show that if this is a given, so if the Hamiltonian translational operator commute, then these orbitals will have the same eigenstate. So the translated orbitals has the same eigenstate. So we can show this by applying this translational operator to an eigenstate, and then the Hamiltonian commuting the both operators. We end up with this, and now we can use this equation applying the Hamiltonian, and we get the eigenstate, and now we have exactly the expression that we want. Hamiltonian applied to this translated orbital gives the same eigenvalue on the translated orbital. So it's an eigenstate of the Hamiltonian. And then we know that we can write these functions with the same properties. So we can express this eigenstate as an eigenstate of the Hamiltonian, which gives you the band index, and of the translational operator. Now we want to find the eigenvalue or describe the eigenvalue of the translational operator. And as we've shown, the eigenvalue, so the energy eigenvalue is the same. So the only way that this can change is by a phase vector. And now we want this to determine this phase vector, and here we want another property of this translational operators is fulfilled, namely that if we translate by two different real space lattice vector, it should be the same as if we translate once by the sum of these translational operators. And one way we can achieve this is simply taking a scalar product, vector product of the reciprocal lattice vector with a new introduced vector, and this vector we will then call the Bloch vector. So now we know that essentially translating the orbitals changes the orbitals just by a product of this Bloch vector times the reciprocal lattice vector. So why do we, so this is kind of more a mathematical way why we can do it, but why do we actually do it in practice? And here we need to consider the computational time that things actually cost. So the main advantage of reciprocal space is that we can treat all these k-points independently. So that means if we want to optimize the orbital for one k-point, is it more or less exactly twice, half the cost than if you want to calculate 2 k-points, or a third of the cost of 3 k-points, and so on. So the scaling with the system size is linear. On the other hand, if we would do the same in the real space, then recall that we use fast Fourier transform to perform this real space transformation. So we always need to calculate certain quantities in real space and certain quantities with the G vectors, for which we do a FFT, and the fast Fourier transform scales predominantly quadratic with the system size. So we gain one order of system size by choosing this reciprocal space technique. Now, this brings me to the outline of this lecture. So now we want to focus in more detail on the k-point sampling. So how do we actually choose these k-point meshes and what impact this has on convergence? Then in the second and third part of the lecture, I will focus on more practical applications. So how to calculate density of states and band structures. So let's focus now on the k-point sampling. So the k-point mesh that you use in a self-consistent calculation is one of the most important convergence parameters other than the energy cutoff. So if you want to investigate certain properties, you should always check that they are converged with respect to your k-point mesh. And here it's really important that you actually consider the quantity of interest. So if you want to converge, let's say, a band gap, you should converge the band gap with respect to the k-point mesh, because other quantities, for example, the lattice constant, might show a different convergence behavior with respect to the mesh. So you cannot just converge the lattice constant and then automatically assume that the band gap is converged as well. So now we want to see how we actually implement this in the code. So in practice, what we do is that we replace real space integrals by going to reciprocal space. So this is essentially a Fourier transform from the real space integral into a reciprocal space one. But of course, in practice, we cannot actually evaluate integrals. So we will then discretize this integral using summation over all k-points with quadrature weights and evaluate these functions. So all functions that we want and that are k-point dependent, we want to evaluate a certain k-points with weights. And now the question is, of course, what k-point meshes should we choose? And it turns out that if you know nothing about a system other than that it is a periodic system, actually equidistant grids are optimal. But of course, equidistant is not always possible, because not always will your system be a perfect cube. So in that cases where you find that your system is not cubic, so where you have longer and shorter axes, what you want to do is then choose your grid such that the grid density corresponds to the length of this reciprocal axis. So more or less the inverse of your real space axis. So what this means in real space then. So that recall that these short distances become the long distances in real space. So this means that we sample this with less points, and k-points essentially correspond to supercells that you consider in real space. So if you consider here a fraction of the reciprocal lattice, reciprocal cell, it corresponds to a supercell in real space. And so this 3x4 mesh that I chose here corresponds then to a 4x3 supercell in real space. And this also holds then for restricted geometry systems. So if you don't have a bulk system, but you have, let's say, a system where, like a surface, where along one direction you have a big vacuum space, recall that in VASP we still describe this as periodic system. So you will still have to choose a k-point mesh for the z direction. But in practice, the way that you do it is you choose only a single dimension along this direction. So essentially, this is also a very long dimension. So this would already suggest that you should vary little k-points, but actually there's another reason to do that. So essentially, this k-points also construct supercells, as we discussed on the previous slide. So what you actually don't want in the surface is that you get some interactions between the surfaces. So by reducing it to a single k-point, occasionally you even get a better physical performance or physical convergence, because you truncate these interactions between the periodic replica. And of course, in plane, you still follow the same rule as before. So that if this, this is a system that is more less cubic. So here you would choose the same direction along both, at the same density along both axes. But you could imagine that in plane, these axes are again different length, and then you would choose again more points along the shorter axis. And this can be also transferred to even smaller geometries. So if you have some wires, you would only use k-point sampling along the direction of the wire. And if you even restrict it further to molecules, you could even calculate with the gamma point only. And recall that in VASP, we have this special gamma point only version. So if your system is very large, or if it's a molecule, and you use this gamma point only version, you can get additional computational speed because the gamma point version. So essentially, we know that if we have the gamma point only, that certain quantities will be real. So you recall this Bloch vector, this e to the ikr. If k is 0, this will be just a 1, so that you can choose your orbitals then to be real. And then you can make the certain function calls call real versions of the matrix multiplication instead of the complex ones. Or FFTs use half of the grid and reproduce the other half, so that you get a speed up. So now let's consider next the symmetry of the system. So the symmetry of the system will determine how many k-points you will actually use in your calculation. So it's important for you to know how VASP determines these symmetries so that you can see how to set up the system properly. Because if you make certain misalignments with the symmetry, you might get worse k-point measures than is possible. So for this particular example, now I will always consider a system where you could imagine it had a fourfold symmetry, but then due to some symmetry lifting, it will be actually reduced to a twofold rotation instead of a fourfold. So the most primitive one is, of course, the shape of the cell. So if your shape of the cell is not a square, but instead a rectangle, you reduce the symmetry to a twofold rotation. So you can see that if you rotate this by 90 degrees, this would not overlap anymore with itself. So this already, the cell of the system breaks the symmetry. But if you rotate it by 180 degrees, then the system is in the same position as before, and you have this twofold symmetry. And then you can use this symmetry to reduce the number of k-points. But there are other symmetries that you need to consider, for example, the atoms. So even if your system or your unit cell is symmetric, so in this case we have a square unit cell, so the unit cell itself would have this fourfold symmetry, but now you can see that the atoms break this symmetry. So if you rotate only by 90 degrees, the gray atom would end up on the red position, so then you have a not the same structure. So you actually need again to rotate by 180 degrees, and then all the atoms end up at the same positions, and then the symmetry is conserved. So this is a symmetry that we can then use to reduce the number of K-points that we need to calculate. But there are more things that we need to consider. So recall that also on these atomic positions, we might have additional vectors that play a role. So for example, magnetic moments or velocities, and these can also lower your symmetry. So here, for example, you can see that we have two different magnetic moments for these atoms. And when you rotate by 90 degrees, you would swap or change the magnetic moment. So even though the atoms are the same, the magnetic moment is not. Or this could be also an antiferromagnet where this is, has the opposite magnetic moment. And then we still cannot use this symmetry. So we still can only use the twofold symmetry. For velocities, you also need to consider that not only do the atoms turn, also the velocity changes the direction. So if you apply the rotation, but so if you set up your system with initial velocities, then you will also, those will be considered for symmetrizing your system. So again, you can see that if you rotate it by 180 degrees, they all end up at the same position. So now what do these symmetries actually imply for the choice of the K-point mesh? So first, let's consider that the symmetry of the crystal also translates to the reciprocal unit cell. So here you can see that if you rotate the real space by 180 degrees, then you can directly also do the same symmetry operations here on the reciprocal space. So let's now consider the implication of this for this 3x4 K-point mesh. And we consider in particular this K-point here in the lower half of this reciprocal unit cell. And then if we turn it around, now you can see that it's not at the same position anymore. Of course, those points can be mapped back by a reciprocal lattice vector to the boundaries. But you can see that some of those points are now, for example, this point here is now here. So those two are actually equivalent by symmetry. That means now that we don't need to calculate both of these points. So we know by symmetry that those orbitals have to be the same up to a phase factor. So now that means that if you do this for all these points, you can see that all these points get actually mapped onto one of the other points. So we only need to calculate actually the dark green ones and not the light green ones. So this, in this case, this would reduce the number of points from 12 to 7. But you can imagine that if you have very high symmetry, a lot of K-points, that this can, and in particular, if you consider also the third dimension, that this might need to lead to a very significant reduction on the number of K-points that you actually need to compute. And recall that the number of K-points is directly linearly proportional to the computational cost. So in this case, we more or less cut the computational cost in half, or almost in half. But there's also one more thing to consider. So in this case, I've chosen the K-point mesh to align with the origin of the reciprocal unit cell. But you don't have to do that. So in principle, there's an arbitrary shift that you can use for this offset. And one very common one is to off-center all the grids so that they are equidistant from the boundaries. And if you do this, you will see that actually you get an even higher amount of points that are reproduced. So if you rotate this, you see that exactly all this upper half are reproduced by this lower half. So you only need to calculate really half of the K-point. So you reduce it by another K-point. So this means that these shifted meshes may actually be more efficient than using using the not shifted ones. However, this also comes at a price, in particular if you have something like hexagonal systems. So in hexagonal systems, so you can see there's hexagons, you have a threefold rotational symmetry. So you can rotate the whole system by 120 degrees and it ends up in the same as before. But if you apply the same symmetry operation to this lower part, or this primitive cell, then you can see that now the K-points are not at the same position anymore. So the rotated K-points are actually not equivalent to the unrotated one. So essentially what this means is that not only can you not reduce the mesh by the symmetry, but actually the mesh is not compatible with the symmetry. So that means that to get a converged behavior, then you would need to use even denser meshes that you normally would use just to restore the symmetry property of the crystal. And actually VASP will write you a warning about that. So if you try to do this, and will suggest that you should use a gamma-centered mesh. And in this symmetries, you should then do this. So in general, we can say that this gamma-centered mesh is then the more robust choice because it will work for all systems. But the price that you pay is that you might use a bit denser meshes that are actually required. So you can reduce your computational time by using off-centered meshes, but this might not always work. And if it doesn't, you need to change back to a gamma point version. Okay, now let's go briefly to a more detailed discussion about this. You should choose your K-point mesh density according to the length in real space or reciprocal space, or inversely to the real space vectors. So actually there are two different ways you can choose this. And for very simple symmetries, those two choices are equivalent. So you can either choose your mesh densities proportional to the inverse length of the real space vectors, or you could choose them proportional to the length in reciprocal space. So the important point is that if this is, let's say, an orthorhombic system, those two choices are the same. However, if your symmetry is more complicated, and if you have vectors that don't have 90-degree angles with respect to each other, then those might be different, and sometimes drastically so, or significantly at least so. What you need to know is that the right side choice is the one that is chosen by VASP by default. So if you don't change it, or if you choose this automatic modes of choosing these grid densities, VASP will choose this particular mode. Unfortunately, there's no unique solution or no unique answer to which of those two is actually the better choice. So it really depends on the system. So for body-centered systems, you want usually to choose this left-hand sides, in particular body-centered tetragonal and orthogonal system, whereas for face-centered tetragonal systems, you should choose this right-hand side. So it really depends a bit on the system, and we have, if you read on the wiki, the section about the K-points, there's a discussion what other things you need to consider when you do this. So if you know that your system has some of these symmetries, so it's not a perfect cubic symmetry, and it's also not a trivial symmetry where there's no symmetry left, but it's some of these more complicated symmetries, then you might want to read up on this section to make sure that you choose the right K-point meshes. Okay, so now let's go more into the practical details, how we actually set up these K-point meshes for VASP. So essentially, the K-point meshes are set in a K-points file. So this is just a text file where the first line is just a comment line. And then in the second line, you specify how many K-points you want, where 0 means that you choose an automatic generation. And then how this automatic generation works depends on the next line. So this the simplest mode is perhaps this mode called auto. So this will choose your k-points completely automatic for you based on this criteria that I mentioned, based on the length of the reciprocal lattice vectors. And the actual density here, which corresponds to how many k-points you choose along each direction. So this is multiplied by the length of the reciprocal lattice vectors and will determine then your grid density. So the larger you choose this, the more points you will get. However, in general, I would probably not recommend choosing this fully automatic mode, except for perhaps some preliminary investigation, because the disadvantage is that as your cell size changes, in principle, this grid can change. I mean, this is perhaps not so common if you don't change it by a large magnitude, but essentially by converting this to an integer grid, there's always some rounding that happens. So at some point you go across this rounding threshold, and then you could end up with a different grid depending on your cell size. So if you want to have a bit more control, you can choose your grid dimensions yourself, and you can do this by replacing this auto with a gamma. So gamma means that your k-point mesh is now centered at the gamma point, so that's the origin of the reciprocal unit cell, and then you specify the grid dimension. So this is essentially these three factors. So this I mentioned earlier. So it's a grid dimension along the first reciprocal lattice vector, second reciprocal lattice vector, third reciprocal lattice vector. This case, of course, is a homogeneous mesh, but if your system is not isotropic, then you want to change this to different meshes. You can then change to this shifted mesh by changing gamma, replacing gamma with Monkhorst, and then we will choose this off-centering of your k-point mesh. So I will briefly mention a few alternatives to this automatic mode. So one is explicitly by specifying the shift. So the most proper usage of this is if you want to mix, let's say, a Monkhorst kind of behavior along certain axes with a gamma or in-plane centered version along other axes. But it's not a very common feature. So typically you would either choose a gamma centered mesh or a Monkhorst centered mesh. Then one perhaps more important choice is that you can choose your generating vectors. So you can replace, instead of using the reciprocal lattice vectors, you can specify your own generating vectors. And this gives you then more control how these k-points are actually generated. And finally, of course, you can switch off the automatic mode altogether and actually replace this 0 with a number, and then just list either in reciprocal space or in Cartesian coordinates the actual coordinates of the k-points. Okay, so this concludes the first section of the lecture, and now we'll focus a bit more on the density of states. So the density of states is a very interesting quantity because it can give you a lot of insight about the system. So just by looking at the density of states here, you can see that, or I mean, we can know that this is a transition metal because of this very compact density of state with high peaks. So then you can also see that there's an exchange splitting. So this already tells you that this is a magnetic system. So this the gap between here, or the shift between here and there, is the exchange splitting. You can see that there's some finite density of states at the Fermi energy. So this means it's a metallic system. And the actual conducting electrons, by looking at the states at the Fermi energy, you can say are of minority spin character. In VASP, we have additional option to inquire where this contribution to the density states actually comes from. And as I already mentioned, so this is a transition metal. So most of this density of states comes from d electrons. So you can see down here, there's a bit of different characters. So this is mostly s electrons, but everything here that is interesting in terms of magnetism and conduction is mostly D character. So let's recap briefly what the density of states actually is. So the density of states is formally defined as the number of states at a certain energy. So in practice, of course, we will replace this exact at this energy by a width, where we say the density of states is the number of states within a certain energy width, but the formal definition uses here a delta function. And then you see that here we already replaced this k-point integral by this k-point sum over all bands and k-points with this k-point weights. And in contrast to the quadrature weights that I mentioned earlier, in this case, because we use this homogeneous measures, actually the k-point weights would all be 1, but then we still get k-point weights by using this symmetry. So essentially, this is the k-point weight is then proportional to the multiplicity of a particular symmetry in the k-point measure. And then in VASP, this density of states is used implicitly define the Fermi energy. So formally, the number of electrons is given by the integral over the density of states until the Fermi energy. And now you can imagine that this defines an algorithm how to determine the Fermi energy. So essentially, we know the number of electrons. So this is given by the podcast files, or the number of the ions and the number of atoms that you use. And then we can calculate the Fermi energy at 2 different levels. So essentially, you can calculate the Fermi energy at a high, or the number of electrons for a very high energy and the number of electrons for a very low energy. And then you see, okay, let's now do an interval bisection. Let's calculate it in the middle. And then in the middle, you would either get too many electrons, then you would set your bisection to the lower part, or you would get too many electrons, then you will take the lower part. So in this way, you successively reduce the width of this interval that you consider for your Fermi energy, and you will integrate until finally the Fermi energy, the number of electrons that you get by performing this integral agrees with the number of electrons that are actually in your system. So now, as I mentioned, there's this delta function in the definition of the density of states. Now in the numerical code, we need to replace this by a finite width. And then there are different ways you can choose this width of this delta function. So, I mean, let's first consider what it corresponds to. So if you talk about real systems, then, or finite temperature, then this would correspond to the temperature. So if you think about this width or this delta function as something like a Fermi-Dirac distribution, or actually to be more precise, the derivative of the Fermi-Dirac distribution, then this would be actually a temperature. And this smearing width would then correspond to the temperature of your real system. But in practice, that's actually not what we typically want to do. So the reason for this is most systems, or in many systems, actually the temperature, so like room temperature, is small compared to the energies that are there in this electronic system. So for us, it's more like a fictitious temperature to make the system converge faster. And then using actually a Fermi-Dirac distribution is a bit disadvantageous, because the Fermi-Dirac distribution has here exponential tails. And so you need to consider a larger energy range here. So by replacing the Fermi-Dirac distribution by a Gaussian distribution, we get actually a narrower peak. And as a consequence, so the decay here is now exponential times energy squared minus energy squared. So this decays more rapidly with the energy. So that means you can consider narrower peaks. And in the end, that means that less states actually are relevant or contribute to this finite occupation. So most of them are either completely full or completely empty. And the advantage of the Gaussian is it's a very robust choice. And so this is what we recommend to use if you have no prior knowledge about your system. One disadvantage is that actually the width of this Gaussian still plays a role. So you need to converge this width to small enough so that it doesn't affect the resulting energy that you obtain. For metals, there's a better choice that accounts for this by using higher orders of, so essentially going to higher orders of this Gaussian type orbitals. So you can see that this essentially has more nodes. So the Gaussian orbital has Gaussian smearing has no nodes, and then it has 1, 2 nodes. So this corresponds to different method choices of this Meffel-Paxton method. You can make this peak narrower and narrower. So this means that less states will actually be occupied. And again, the same argument as between Fermi, Dirac, and Gaussian smearing applies here. So if you can make this peak narrower, it leads to a more robust or faster convergence. However, there's one disadvantage of this Meffel-Paxton method, and that is comes here from the fact that actually this weight function goes below 0. So this means that here actually some states will have negative occupancy. And this is of course unphysical. A physical state cannot have been negatively occupied, so you can only have a positive number of electrons in it. So but for metals, actually, this doesn't matter, because for metals, you have a continuous band across the Fermi energy. So these states that are here negatively occupied are very similar to the ones that will be occupied here. So in the end, the density that you get by doing this approach is not really affected, because the states are have very similar densities. However, if you do insulators where there might be a band gap here between, and the states that you then occupy here and the states that you might empty on the other side might have different orbital characters, you might corrupt your density, and then you don't get the proper ground state density anymore, and then you get incorrect results. So this is why for insulators we have a different approach. We the so-called tetrahedron method. So essentially the tetrahedron method corresponds to mapping your energies, or you can split the K-point mesh into tetrahedra. So every little fraction of your every little fraction of your grid is split into 4 corners, and map the sort then the order the energies at the corners in increasing order, and then you actually only occupy the states, only occupy this tetrahedra if the Fermi energy is between the lower and the higher bound of this tetrahedra. So the advantage of this method is that you actually only occupy this tetrahedron if it's in the energy range of the Fermi energy. But there's a disadvantage, and this comes if you not only want to consider the occupation of the whole tetrahedron, but now want to focus in particular on the weights of these individual corners. And this is that if you apply this Blöchel corrections, which gives you the most accurate occupations, then actually the derivatives of those are not variational. So that essentially means that if you move your atoms, there might be a discontinuous change of these occupation factors. So that means you cannot calculate accurate forces. So this is why this is why you shouldn't use it for metals. So in insulators, essentially your occupations are either 1 or 0, so then it doesn't matter. But for metals, where you might have fractional occupations, you should not calculate forces with this tetrahedron method. Okay, let's compare these two different approaches on one slide. So I already mentioned that here in this interpolation method, you only occupy what's actually below the Fermi energy and nothing above. Whereas in the smearing method, you can now imagine if you had the same 3 K-points, you would also occupy all the other ones a bit. So it really depends a bit on your width. So you can imagine that if you have a very narrow tetrahedra here, that would be completely above the Fermi energy, it would not be occupied. but the smearing width is the same for all k-points. That means even a k-point that is even corresponds to a very narrow tetrahedron will still be occupied if you smear with Gaussian or Monkhorst-Pack method. So this is particularly noticeable in the density of states, which makes the tetrahedron method, where this doesn't appear, particularly well suited to describe density of states. So that means that even if you calculate a metal where you might not want to use the tetrahedron method, you could still use it as a non-self-consistent run just to get a very good density of states. Okay, let's now focus a bit how we set this up in practice. So the default in VASP is actually the Monkhorst-Pack smearing. So if you don't specify anything, VASP will assume this I-smear flag that determines the smearing method will be set to 1. Then if you don't know what you do, what the system actually is, you can override this default by setting it to 0. So this would correspond to Gaussian smearing. But recall that for a Gaussian smearing, you need to change also the smearing width, and this is controlled with this sigma parameter. Finally, the tetrahedron method is selected by setting the smearing to -5. And then this you can do for example, density of states or insulators. And there's also this extra option that I mentioned in the introduction of this section, that you can set this orbital projection method. So you do this by setting L orbit to 11 or alternatively 10. So this is L resolved or LM resolved. You will again get L resolved or LM resolved density of states. So this brings me now to the last section. We will now talk about band structure calculations. So band structure calculation is another way to get insight about the system. So in a band structure, you can resolve it by the orbitals of your, or the spin character of your orbitals. So you can again see here a spin splitting of your different orbitals, but in addition, it also gives you a k-point resolution of your energy. So you don't know just what states are where, at what energy, but also which Bloch vector they correspond to. So this is in particular interesting if you do transport properties or some, let's say, scattering properties where you want to excite from one state to another with light, then you're only allowed to do vertical transitions. So then you can use this band structure information to get more insight about your system. Again, you have this orbital projection method. So you can resolve, for example, how much s orbital is in these different bands, and then you can find out that not only that these low energy ones have, so this lowest band has s character, but it only has s character near the gamma point. So actually, if you follow the band here, it gets intermixed with the d bands. So there's some hybridization going on, and then probably you would see that the s band actually continues up there. So these are d bands, and this is the s band. So then in the band structure, a very important thing is that you have these high symmetry lines. So you typically specify some high symmetry points in the Brillouin zone that you want to use to construct your band structure. And now in the next few slides, I will show a bit how you can actually choose these high symmetry lines. So first, let's recall what these high symmetry lines actually correspond to. So this is now a supercell of the reciprocal unit cell. And now what we do is we construct the Wigner side cell of this. So this is then called the Brillouin zone. So that's the first Brillouin zone. So this is if you go along this axis and then take the perpendicular bisector and then do this along all axes and also in the third dimension, you will get this intersection. And now the high symmetry lines correspond to following these lines along particular paths. So usually you go from the center of the cell to the boundary and then follow the boundary and go back to the center. For example, you could choose this kind of path. But of course, in practice, you don't want to do this yourself. So you essentially those symmetries of the space groups have been studied for a long time. So you don't need to redo all the work here. So you can actually use tools to do this. And then here I want to present two tools that you can use. So one is the Bilbao crystallographic server. So if you want to get information about K-points, there's one section in the space group symmetry, which is called KVEC. And you can the K-vector types and Brillouin zones of space groups. So this will then list a number of points, of high symmetry points in particular space groups. So the only thing that you need to know is the space group of your system. One even more hands-off approach is the seek path. So in the seek path tool, you can even upload a POSCAR file and then calculate the structure. So it will analyze the symmetry of your structure and then directly produce a possible high symmetry, or even suggest which high symmetry points you should use for this particular structure. So there's one disadvantage of this approach is that you rely on the symmetry analysis that is built into this tool. So me personally, I prefer a bit the approach of analyzing the symmetry myself so that I can really see how this depends on the symmetry, on the choice of the precision that you do in the symmetry analysis, and then do it based on the space group, which, by the way, you can also do in seek path by doing this lower one. So you can specify the symmetry explicitly at the bottom. But if you prefer this all built-in approach, there's also the choice to provide just the POSCAR. You just need to make sure that your POSCAR is precise enough. So any symmetry analysis relies on some precision. That's also true for the analysis in VASP, of course. So if you don't specify your crystal precise enough, your symmetry analysis will fail. Okay, so let's go then in the practical parts. How do we specify this K-point meshes in the K-points file? So what you do here is you set the number of K-points. So this in this instance corresponds to the number of K-points per line segment of this high symmetry line. So for each part, let's say from gamma to L, you would use 40 points, and then from L to M, you would use another 40 points. And then the second important part is you replace this second line with line, and line means this line mode. So we will only generate K-points along these lines. And then you set this to reciprocal. So reciprocal is perhaps here the most common choice. So that means that you specify your coordinates here in multiples of the reciprocal lattice vectors. And then the last points are just each line. So you give the coordinate of each line. So this might be L, this is gamma. So this depends now on what you found in this symmetry analysis tool. So one thing I should stress here is what you need to do is you need to freeze your density of states, your density, so your charge density. So the K-point mesh that you use for this band structure calculations are not suitable to get a good density. So that means if you would use this K-point mesh in a self-consistent run, your density would look drastically different from a ground state density. So that will have completely different physical properties, and you would get a wrong band structure out of it. So always remember that you set this I charge 11 in the incar file, then it will take the density from a previous self-consistent run that you optimized with a regular K-point mesh, and then you get a proper converged band structure. Another thing to consider is hybrid functionals. So hybrid functionals are special in a sense that you calculate the self-interaction or the self-energy, exchange self-energy. And the exchange self-energy, to evaluate this, we require a regular K-point mesh. So this means that traditionally the K-point mesh that we had to use for hybrid functionals always had to include the regular mesh, and then in addition the K-points that we wanted for our band structure. But now in VASP 6.3, we introduced a new feature that you can of course also use for regular band structure calculation, which is called K-points opt. And this K-points opt feature is now a new approach to do this kind of calculations. So we have the conventional K-points file that you always use for your self-consistent calculation. So this is iterated and reused And this is good for using, for example, the density. You can also get the density of states out of it. But then after this is converged, we will do a non-self-consistent run with a separate KPOINTS file. And this is the KPOINTS opt file. So it's an optional KPoint mesh that you only use in a one-shot calculation. So you might use this for effective masses, but perhaps the most common application of this we expect will be band structure calculation. So the idea is you do a density of states, or your density of states calculation with a dense K-point mesh, and then just do a single run to get the orbitals and eigenvalues at this extra K-point mesh. And the way that you do this is you just provide this K-points opt file. So that's the only thing that you need to do. It has the same format as the K-points file. So if you provide one of these line mode band structure files, it will directly produce you the band structure in a single calculation. And already the presence of it will trigger this treatment of this optional K-point meshes. And this also works with hybrid functionals. So you can now use a self-consistent way to calculate the hybrid functional self-energy, the exchange self-energy, and then just say this K-points opt file to get the band structure. Okay, this brings me to the end of the lecture. So we discussed a bit how to choose the K-point sampling and its implication for the converging the structure and how symmetry affects the choice of your K-point mesh. And then we looked at two practical examples, how you can choose smearing methods and K-point meshes to get good density of states, and how to get the high symmetry paths to get band structures. Thank you for your attention. I'm happy to take your questions.
Thank you for this very nice talk. That was a lot of information about K-point sampling and also practical aspects like the density of states and the band structure. So I will immediately ask some question from the audience, if that's all right.
Sure.
There's a user, my system is a bulk semiconductor, and I know that the band gap is at the gamma point. So I only want to know the band energies at the gamma point. Is it okay if I just use the gamma point version of VASP?
I mean, this goes a bit back to the same argument that we had with the band structure. So essentially a single K-point will probably not give you a good density. I mean, of course, it depends on the size of your system and things, but in general, what you always want is first to get a good density. So that's the kind of the first part of the relaxation or self-consistency, is get a good electronic density. And then the next part is then calculating the band structure for this density. So if your gamma point is not good enough to give you an accurate density, you will get a completely different band structure. So essentially, I mean, of course, it depends on your system, but in general, this will not work. So the only way this works is if you, for some way, magical way, know the density in advance. So then you could do that.
Okay, so I think we can go on to the next question. That was pretty clear. I don't understand space group symmetry so well. So this user maybe not an expert in that field. So when I set up a K-point mesh with the Monkhorst-Pack method, should I choose even or odd number of K-points?
So with the Monkhorst, okay, so in general, if you want to use Monkhorst mesh, and if you choose an odd numbered mesh, then it will actually correspond to the same as the gamma point mesh. So in that sense, then there's no difference between the Monkhorst and the gamma centered meshes. If you choose an even numbered mesh, then you will see this off-centering of the cell, which can then lead to the symmetry breaking. So in terms of robustness, using even numbered meshes or gamma centered meshes with, using odd meshes or gamma centered meshes is perhaps a bit more robust in terms of high throughput calculations.
So the important point is that this user uses the gamma-centered mesh, and that is easy to.
I mean, if you do high throughput, I would probably always use gamma-centered, because then you have the freedom of choice to use also the odd-numbered meshes. Whereas if you use a Monkhorst mesh, you need to take care that it's compatible with the symmetry.
Mm-hmm, mm-hmm.
I mean, if you a single system, of course, sometimes this 10% or so speed up that you get by using a Monkhorst mesh might be the thing that pushes you to use the Monkhorst mesh. But if you want to study 1,000 systems, then probably the extra effort to investigate why do now 10 systems not work because of the symmetry, it's probably more time effort than using always a gamma mesh and spending 10% extra compute time.
Mm-hmm, mm-hmm. Particularly human time, very
human time
valuable resource. So there's another question about the KPOINTS opt file, this new file that is available from VASP 6.3. What's the difference to using the IBZKPT file? So this KPOINTS in the first Brion zone, I think, is why this file is called like that.
Yeah, so the IBZKPoint file is essentially the result that VASP interprets from your KPOINTS input file. So this is, in the end, if you want, this is how VASP analyzed your KPOINTS, how it interpreted it, and this is something you can check to analyze which KPOINTS actually you want to use. But the way that this works is the KPOINTS opt file is really more on the side of the KPOINTS file. So I mean, of course, the IBZKPoint file can be used as a KPoints file, so you could reuse it. So let's say if you have a IBZKPoint file that describes a band structure calculation, you could copy that to a KPoints opt file, and then it would do a KPoints opt calculation. But in principle, in terms of setup, so if you want to set it up manually, setting up the KPoints opt file is the same effort as setting up a KPoints file. So it's really, yeah, it's the same format, it's the same language. And if you have this band structure mode, then I think it's probably easier to set this up in the KPoints file than to explicitly list all the KPoints. I mean, this IBZKPoints file, I think traditionally was more important for hybrid functionals. So you could get more or less a list of this band structure path and could then add this to a regular mesh or merge to IBZKPoint file to get the right mesh to perform this hybrid functional calculation where you did both band structure and getting the right self-energy, Hartree-Fock self-energy out of it. But I think in the future, I would probably suggest that users use this KPoints opt features for hybrid functionals. And in particular for hybrid functionals, it seems a real advantage over the old method.
Yeah, so maybe so IBZKPoints writes the KPoints that were used during the calculation, so that implies that there was also already a calculation run before. And maybe the misunderstanding is that the KPoints opt file can actually be used as an input file right from scratch. So there's just a single shot calculation in the end of your self-consistent run, but you don't have to restart VASP to do that. So that is
yes, that's exactly how it works.
Okay, so hybrid functionals was already a very good keyword. How do you set up the KPoints mesh for a hybrid calculation? So there are now multiple ways, right? The KPoints opt file you already mentioned. So what is the traditional way to do it?
Okay, so let's perhaps go a bit more in depth how you calculate band structures for hybrid functionals. So as I mentioned, you need to get a self-energy operator. So essentially there are two traditional ways to do it. And then there's now this new way with this K-points opt file. Let's go briefly over the two traditional ways. So you can calculate a self-consistent run, and then you can construct one-year functions from that, and then do your one-year interpolation. So this requires, of course, you then to have this external tool, so one-year 90. And this also has, of course, other issues that you need to know which bands should I one-yearize, and then you need to choose the right one-year window. And so it's also not trivial to do this one-yearization. But if you do that, then you can use those one-year functions to interpolate your band structure. And for a coarse band structure, that will look probably fine. If you do more detailed band structure analysis, so let's say for effective masses, or just something where it's very crucial how the bands actually look like, so you want to really have the DFT precision for your band structure, then you would need to do the second approach, which is to actually list additional K-points. So essentially, here this IBZKPT file would come into play. So what you can do is essentially think, or which K-points do I need? So you can set up a calculation. Let's say you can just do this on the PVE level, where you produce a regular mesh for your structure. So then you store this IBZKPT file, then you set up a band structure for this particular system. You get another IBZKPT file, and then you merge those two IBZKPT file into a new K-points file where you explicitly list all the K-points. And then the regular mesh, you use the same weights that they had in the regular calculation, and all the weights of the band structure path you set to 0. So essentially that means that you calculate a few K-points with the same computational cost as calculating those K-points, but with 0 weight. So they will only be evaluated, but don't contribute to the density. And yeah, and then in the end, you analyze the eigenvalues of this the results, but throw away all the ones that correspond to the regular mesh, and then plot the band structure through those eigenvalues. I mean, you can see that this is a bit more involved than just adding a new file K-points out. So for this new way of just setting up, I mean, essentially you already had to do the same work, right? So in this previous work, you had to set up a K-points file for a regular grid. You had to set up a K-points file for the band structure mode, but all this manual work of combining those files, then using the IBZKPT file into one file that works as a K-points file for the whole calculation is now gone. So this is something the code will take care of.
Okay, so the central issue is that even though I only want to compute the band structure, I always need a regular K-mesh to also compute the Fock exchange, which is part of any hybrid functional. I see. And so with that respect, there is actually a related issue to or tag, let's say, that would be to perform some downsampling. So use a coarser K-mesh for the Fock exchange. Can you extend on how one could do that?
Yeah, so this perhaps goes back to the point that I made here with the K-point sampling, that different quantities have different conversion speeds in reciprocal space. So and what one notices is that actually the self-energy, so the Fock self-energy, converges more rapidly with K-points than other physical quantities like the density. So then the idea is, okay, can we not use less K-points to sample this Fock exchange and still get good results? And actually it turns out that this kind of naive way actually works. And in particular, it works well for range separated hybrid functionals, because then you actually truncate the interaction in real space. So that means that in reciprocal space, again, you don't need to describe it so well. And the way that you do this is then that you can specify this NK red flag. So this means number of K-points reduction. And then you can set for each direction how much you want to reduce it. So you can either set it globally for all directions or specifically for each direction. And then you could say, okay, I want regular mesh, I want to do 12, 12, 12. And then the self-energy, the Fock self-energy, I evaluate on a 666 or 444 mesh. And yeah, and for hybrid functional calculation, it's really evaluating this hybrid functional, this Hartree-Fock exchange is the most costly part of the calculation. So the calculation with this 12-12-12 reduced to 666 might be as expensive or similarly expensive to a 666 hybrid functional calculation. So it's really an important point. Of course, you sacrifice a bit of accuracy, but I mean, that's always the case. You have to make a compromise between what can you realistically achieve with the computational resources that you have available and the accuracy that or precision that you get out of your calculation.
Yeah, and hybrid functionals, they really take a lot of computational effort. So this might be a very important step for production calculations for real research applications. So thank you very much for the talk and also for the very nice explanations in the end. They went into a lot of details as well. So thank you very much.
Thank you.